Okay, so thank you very much, Daniel, for the nice presentation. Okay, so ladies and gentlemen, welcome to this session on magnetocaloric refrigeration. So the title of my presentation is quantum materials for not only hydrogen but also helium storage. So at the beginning, I will to give you briefly some evidence about magnetocaloric effect, magnetic refrigeration, and some relevant advanced magnetocaloric materials. Then after, I will present some interesting result obtained with in relation with magnetism and magnetocaloric effect obtained in some very promising magnetocaloric compound that can be applied in cryogenic refrigerations. These materials particularly belong to two interesting family of oxide. The first one is, sorry, I'm looking for the pointer. Okay. So the first one belongs to the raw earth manganese, and the second one to raw earth vanadium. Then I will finish by conclusions and the perspectives. So as already introduced by Daniel, magnetic refrigeration has attracted a worldwide interest, particularly over the past 2 decades, of course, due to its higher efficient, eco-friendly character. So with magnetic refrigeration, we can also cover a wide range of application, going from heat pumps to cryogenic refrigeration, including, for example, the liquefaction of hydrogen and helium. So this technology is based on the magnetocaloric effect. Donc Daniel already discussed the physics behind the magnetocaloric effect. But what I can say is that this magnetocaloric effect can be directly measured by a system of thermocouples, as you can see here, or indirectly determined from specific heat measurement and magnetization data. However, due to the challenging character of calorimetric measurement, the magnetization method is widely used to determine the magnetocaloric effect, particularly in terms of the entropy change. So in this case, all what we need is to perform some magnetic isotherms around the ordering point of the materials. Then after, the entropy change can be determined by numerically integrating his isotherm using the wheel number. There is an interesting point that I want to mention, is that the temperature of magnetocaloric materials make more efficient and serious magnetocaloric device. So fortunately, this magnetocaloric effect in a refrigeration process can be amplified by using some specific thermodynamic cycles called IMR cycles, active magnetic refrigeration cycle. And in a magnetocaloric device, each IMR cycle breaks up into 4 steps. The first one consists to maintain the material increasing its temperature. Then after a high transfer fluid, for example, water, flow from one side to other side of the materials to evacuate heat. Then after the material is demagnetized, decreasing its temperatures, and finally the same high transfer fluid flows in the opposite directions to evacuate cooling energy. So after each IMR cycle, the temperature of the cold end decrease, and that of the hot end, increase to reach a steady state after a certain number of IMR cycles. This is the principle of magnetic refrigeration. So currently, the gadolinium metal is the material used in the vast majority of magnetic refrigerator. However, the gadolinium is very, very, very expensive. In addition, it oxides easily. Okay, so the utilization of gadolinium as a refrigerant in a wide range of application, a wide range of commercialization is out of questions. Okay, so to deal with these drawbacks, a huge effort was made by the magnetocaloric community, leading to major advances in the late of 90s, particularly by Pisharsky and the late Carl Schneider. In fact, both scientists discovered a giant magnetocaloric effect in this family of compound germanium silicon based materials that can be used as a refrigerant in room temperature application. And as you can see here, a few years later, other interesting materials from both performance and economical point of view were reported, including this very interesting family just deeply discussed by Professor Daniel Fauchard. But today I will not talk about materials that can be considered for room temperature application, but I will more focus on materials for cryogenic temperature range that is also very important from practical point of view. Okay, so for more information about magnetic refrigeration as well as magnetocaloric materials for room temperature applications, I refer the interested reader to this review paper recently published in Applied Physics Reviews. Okay, so why materials for cryogenic application? In fact, this sort of materials are also highly important from a practical point of view, so they can be used in some specific application, such as the, for example, the liquefaction of hydrogen, helium, space industry, and scientific instrument. Here is shown a magnetic refrigerator dedicated to the liquefaction of hydrogen, recently, unveiled by a Japanese team a few years ago. So in the developed magnetic refrigerator, a magnetic garnet, a magnetocaloric garnet, okay, shown here, is used in an IMR cycle to achieve the refrigeration process. However, as you can see here, this family of garnets in vial moderates magnetocaloric properties, particularly in terms of the adiabatic change that reach only 1 to 2 Kelvin under a magnetic field change of 1 Tesla. So in this context, it is necessary to search for more advanced and performant materials for cryogenic application. And in this way, this family of oxide, which are rare earth manganese and rare earth vanadate, could be serious alternative to garnet due to their outstanding magnetocaloric properties in the temperature range under 50 Kelvin. So in the following, I will try to present some interesting results in relation with the magnetism and the magnetocaloric effect in some selected compound belonging to both families. And I will start with the rare earth manganate multiferroics. So in this family of multiferroics, this family of materials has attracted a worldwide interest, during the recent years, because mainly of the strong coupling between their magnetic and electrical ordering parameters. For example, in this famous work published by Hoare and co-workers in Nature, it was clearly shown that the electrical polarization of the terbium compound can be easily switched by using not electrical field, but by using a relatively low magnetic field of about 2 Tesla, opening the way for the implementation of this family of multiferroics in spintronic device. So this is very important. So if you look here, this family of materials usually crystallize in a very complex orthorhombic structures composed of octahedra and pyramids. So in these crystallographic structures, particularly the pyramids share their edges to form chains along the z-axis of the crystals, okay? While the formed ribbons are linked by pairs of pyramid, as you can clearly see in this figure or this figure. You know, the pyramids, the ribbons are linked by pyramids in the AB plane, while the rare earth elements shown here occupy the empty seat surrounded by octahedra and pyramids. So this is the crystallographic structure of this family of multiferroics. It is worthy to mention that, you know, the competition between different exchange interaction in this compound involving both rare earth and the manganese lattice lead to a wide variety of phase transition, as can be clearly seen in these figures representing the specific heat as a function of temperature. So consequently, in these materials, an uncommensurate antiferromagnetic state involving the manganese sublattice occurs at a temperature of 45 Kelvin. So this incommensurate antiferromagnetic state gives rise to a ferroelectric order in these materials at around 38 Kelvin. On the other hand, this incommensurate antiferromagnetic state transforms into a commensurate antiferromagnetic state at 33 Kelvin, then again becomes incommensurate at the temperature of 20 Kelvin. Concerning the rare earth elements, their magnetic moment, they usually order at temperatures below 15 Kelvin. Also, there is an important point that I would like to mention concerning this family of materials. In fact, the magnetic moment, the magnetic moment of the manganese sublattice are strongly antiferromagnetically coupled in the A-B plane, forming zigzag as shown in these figures. So this makes the contribution of the manganese lattice to the wall magnetization of the materials marginal. Consequently, in this family of compound, the wall magnetization is contributed from the rare earth element. So consequently, the magnetocaloric effect is also directly contributed from the ordering of rare earth element magnetic moment. Also, the strong, interaction between the manganese and rare earth element magnetic moment lead to a giant magnetic anisotropy, as can be shown in this figure with clear, hazy, and hard magnetization axis. So from this figure, we can see, for example, that along the hazy axis, the holmium and terbium compound, unveil a large magnetization values, while along the hazy axis, the magnetization is very low. So this means that large magnetocaloric effects can be expected in this material by magnetizing them using external magnetic field along their hazy magnetization axis. Also, the strong anisotropy between their hazy magnetization axis and the hard magnetization axis will lead to additional thermal effect that can be obtained not by magnetizing and demagnetizing these materials, but by rotating them in a constant magnetic field, which is very, very important from a practical point of view, because with such rotating magnetocaloric effect, you can make more efficient, compact, and simplified design for magnetic refrigeration. So, this family of multiferroics is very important from a practical point of view. So in addition to large conventional and rotating magnetocaloric effect, this compound usually present an insulating behavior because they are magnetoelectrics. This will enable us to prevent thermal losses caused by eddy current between magnetizing and demagnetizing these materials in magnetic refrigeration systems. Also, the strong coupling between magnetic and electrical ordering parameters in this compound will enable us, for example, to control the magnetization and accordingly the magnetocaloric effect by using electrical field instead the external magnetic field, which is also very important from a practical point of view. Also, these materials are chemically stable because they are oxide. Then also due to the to several degrees of freedom existing in this family of materials, there is a possibility to build multifunctional devices. Sorry. Okay, so here is given the magnetocaloric effect in terms of the entropy change along the main crystallographic axis of the aluminum compound. As you can see here, the entropy change generated by this compound present a strong anisotropy. We can see that these materials involve a giant magnetocaloric effect, particularly along its AZ axis corresponding to the B direction. This giant magnetocaloric, sorry, I am searching for the pointer. Okay, this giant magnetocaloric effect is located over the temperature range around 10 Kelvin, which is the helium, while along the hard axis corresponding to the C direction, this materials, as expected, involves moderate magnetocaloric effect in terms of the entropy change. Here is another interesting magnetocaloric oxide that can be considered for cryogenic applications. This material is the terbium manganese. Here is shown its entropy change along the AZ axis corresponding to the A directions, the intermediate axis corresponding to the B directions, and to the hard axis corresponding to the C directions. So similarly to the aluminum compound, these materials involve also a giant magnetocaloric effect in the temperature range around 10 Kelvin. However, in contrast to the aluminum compound, the terbium manganese involves giant magnetocaloric effect and a relatively low magnetic field. So this is very important from a practical point of view because such relatively low magnetic field can be reached by using permanent magnets. Okay. Along the hard magnetization axis, so as expected, the entropy change is marginal. So this difference in the magnetocaloric effect between the terbium and the aluminum can be mainly attributed to the difference in the magnetic behavior of their magnetic moment. Magnetic moment, presents a ferromagnetic-like behavior, while in the aluminum compound, these magnetic moments, present a paramagnet, like magnetic behavior. Also, as we can see in, so as can be also seen clearly in this figure, the terbium compound involves a giant anisotropy of magnetization. This also would explain the marginal value of the entropy change along the C axis. So as I explained before, in addition to this conventional magnetocaloric effect, this family of compound present a giant anisotropy of magnetization and magnetocaloric effect. So in addition to the conventional magnetocaloric effect that can be obtained by magnetizing and demagnetizing these materials, additional caloric effect can be obtained by, as shown here, by rotating their single crystal between the AZ and hard magnetization axis. So in this case, the associated entropy change, the rotating entropy change, is simply the difference between entropy change along the AZ axis and the entropy change along the hard magnetization axis. Okay. In this slide is shown the rotating adiabatic temperature change in terms of both entropy change and the adiabatic temperature change reported for terbium and holmium under a magnetic field of 2 Tesla. We can clearly see that terbium compound involves better performance in terms of both entropy change and adiabatic temperature change. So, for example, in a magnetic field of 2 Tesla, the rotating adiabatic temperature change shown by terbium compound is 5 times larger than that of holmium materials. It is also worthy to mention that the rotating adiabatic or the adiabatic temperature change shown by terbium compound is more or less 5 times larger than that shown by garnet materials that are usually used in magnetic refrigeration at low temperatures. So this will open the way for the implementation, particularly of terbium compound in cryogenic magnetic refrigeration. So as I explained before, such as difference between the magnetocaloric properties of terbium and holmium compound are mainly attributed to the difference in the magnetic behavior of terbium and holmium magnetic moment, in addition to the strong magnetic anisotropy shown by the terbium compound as clearly seen in this figure. There is another interesting point. In fact, in addition to all these factors, the specific heat of terbium compound is much lower, as you can see here, than that inviolate by the holmium compound. And this is mainly due to the fact that the magnetic moments of terbium compound are more ordered, so lowering the contributions from the magnetic specific heat. Okay, so for more information about this family of materials, particularly the physics behind their magnetic, electrical, and magnetocaloric properties, I refer the interested reader to this review paper recently published in Crystals. And now I move to the another interesting magnetocaloric family that can be considered for low temperature application. So in this part, I will present some result obtained with the terbium vanadium compound. You know that this compound, the terbium vanadium compound, belongs to the rare earth, to the family of rare earth vanadate, that is still attracting a worldwide interest, okay? Particularly because of their fascinating, not magnetocaloric property, but their fascinating optical properties, since they can be used for example, as polarizer or as laser materials in several devices. So this family of compounds usually crystallize in a tetragonal zircon-type symmetry at room temperature, as shown here. Then this tetragonal structure transforms into an orthorhombic symmetry at temperatures below 40 Kelvin. This crystallographic transition is usually associated with a Jahn-Teller effect due to the strong coupling between the electronic order of rare earth element and the crystallographic structure. Such a transition is very, very important from a fundamental point of view because it determines the magnetic, electrical, the magnetic, the magnetization, the magnetic anisotropy, as well as the rotating magnetocaloric effect in this family of compound. In fact, when lowering the crystallographic symmetry from tetragonal to the orthorhombic structure, we observe a marked change in the crystal electrical field configuration. And this change in the crystal electrical field configurations lead to a large magnetizations, usually along the A-axis, associated with a strong anisotropy, magnetic anisotropy, and also magnetocaloric anisotropy. Okay, so what about the magnetic order? Usually this family of materials involves a weak magnetic order even at very low temperatures. And when it exists, the rare earth vanadate compound usually experience a magnetic order at temperatures below 4 Kelvin, as can be clearly seen here for the dysprosium compound. In the case of terbium vanadate, a non-ferromagnetic ordering takes place at temperatures below 1 Kelvin. Now I will show some results concerning this compound. So here is given the magnetization as a function of temperatures for the terbium vanadate compound reported along both the A-axis and C directions. So as can be seen in this figure, the magnetizations involve G and anisotropy with the magnetization axis along the A directions, and on the other hand, a rapid magnetization, we can hear around 33 Kelvin, we can observe a fast change in the magnetization. And of course, this fast change in the magnetization is due to the lowering of crystallographic symmetry from tetragonal to the orthorhombic structure that take place exactly at 33.1 Kelvin. And of course, this structural transformation associated with a cooperative Jahn-Teller distortion give rise to, as can be seen here, a large magnetization along the A-axis and a strong magnetic anisotropy in these materials. So this crystallographic transition, which is associated with Jahn-Teller cooperative distortions, is confirmed by this Raman scattering data reported in this figure, where we can see that under temperatures of 33 Kelvin, we can see clearly splitting in some energy levels. Okay. Here is given the entropy change as a function of temperatures in the terbium compound along both the AZ axis and the harmonization axis. So particularly G and magnetocaloric effect is observed in these materials at very low temperatures. Particularly temperatures around 5 Kelvin. For example, in the magnetic field change of from 0 to 2 Tesla, the entropy change reach a value of 20 joules per kilogram Kelvin. But more importantly, this giant magnetocaloric effect remain approximately constant over a wide temperature range, okay? As shown here, particularly under significantly high magnetic field. This is very important from a practical point of view, particularly when using some specific cycle to achieve the refrigeration process. For example, the and the Ericsson thermodynamic cycle. And of course, this wide range, this large working temperature range under high magnetic field leads to a record refrigerant capacity for terbium vanadate. Okay, here the refrigerant capacity, of this compound is compared with some of the best magnetocaloric materials that can be considered for cryogenic applications. The refrigerant capacity is really a very important parameter because in addition to the magnetocaloric effect, it takes 2 minutes.
2 minutes.
I will finish.
Okay.
Yeah, 2 minutes. I will. Thanks, Professor Zaz. Okay, so this refrigerant is very important because it takes into account both the magnetocaloric effect in addition to the temperature, the working temperature range. In other words, the refrigerant capacity measures the energy that can be transferred in an IMR cycle between the hot and cold ends. Also, as expected, you can see here that the material present a strong anisotropy of the magnetocaloric effects. So accordingly, the materials also involve large rotating magnetocaloric effect that are similar to the conventional one. Okay. Of course, this rotating magnetocaloric effect, as shown here, can cover a wide temperature range, going from 50 to 0 Kelvin. So for more information about particularly the information on how the crystalline field acts on the magnetic and magnetocaloric properties of the terbium vanadate compound, so please, you can take a look at this very, very, very interesting paper just published a few days ago in Physical Review Materials. This work was done in close collaboration with my colleagues from Taiwan, from Sherbrooke University, and from the Bulgarian Academy of Science. And now, sorry, Professor Zaz, I come to conclusions. So as shown in this presentation, some of the raw earth manganese and raw earth vanadate involve excellent magnetocaloric properties at cryogenic temperature range, opening the way for their application in the liquefaction of hydrogen and helium, for example. Okay? Particularly, the terbium vanadate compound involves a large magnetocaloric effect over a wide temperature range, which is highly appreciated from a practical point of view, particularly when using IMR and Ericsson cycles. Also, these materials show high level of rotating magnetocaloric effect in the temperature range under 50 Kelvin, opening the way for the amplification, the implementation in more efficient, compact, and simplified magnetic coolers. However, the big challenge remains the growth of single crystals in a large quantities. But fortunately, textured powders and their magnetic field will be a serious solution, since this oriented powders would play, would behave like a single crystals. So that's all, folks. Thank you very much